Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about the topological analogue of the notion of an algebraic closure of a field, or actually more precisely the separable algebraic closure of a field. And that topological notion is called the universal covering space. So before beginning, unfortunately, we need to assert some extra hypotheses on the topological spaces that we're going to work with. And the useful ones here are the following. So firstly, often we'll want to look at things which are connected and locally path connected. And also eventually we'll need to also assert that the topological spaces are similarly simply connected. So if you're not so familiar with these sorts of conditions, I guess one good example to keep in mind are the manifolds. Okay, so if you have a connected manifold, it will satisfy these. So this theory that I'll present in this video will apply to manifolds. Okay, so firstly, let's define the universal covering space. Suppose X here is a connected, locally path-connected topological space. And we have a covering projection, okay, pi from X tilde to X. And suppose this X tilde is simply connected. In that case, we'll say that this X tilde, or more precisely, the actual map pi, is a simply connected cover of X, or a universal cover of X. Okay, so that's two different terminology for the same thing. Okay, so let's just look at a simple example. So what we know, so here we have R. There's a quotient map to the quotient group R mod Z, and this R mod Z is also a topological space isomorphic or homeomorphic rather to the circle. So this is going to be, in fact, a cover, okay, a covering projection of the circle. And since R is simply connected, this is a simply connected cover or universal cover. And so that's drawn, illustrated here. And that's easy enough to see this example. So certainly it's clear why we call such a cover a simply connected cover, but why is it called a universal cover? Okay, so in this theorem, I want to sum up some facts about such a cover. So suppose you have a universal cover pi from X tilde to X. Well, then it is indeed universal in the following sense. Okay, it's universal in the sense that suppose you're given another connected cover, say from Y to X. Okay, so here you have your universal cover from X tilde to X by pi, and here you have another one from Y to P. Then you have a map of covers from X tilde to Y. In other words, you have a map from X tilde to Y such that the following diagram can be used. So in the sense, this universal cover is indeed the mother of all connected covers. The other thing is the connection with Galois theory. Okay, so one of the things that we saw in the video on lifting properties, okay, of covers is that if you were given cover, okay, so you have an action of the fundamental group downstairs on fibers of the cover. So this will act on any fiber, okay? And in this case, what will happen is that we will have an action not only on just all the fibers, but on the whole space. So the fundamental group part 1x, okay, we're assuming downstairs this is connected, so and path connected, and so that means that all these fundamental groups, it doesn't matter what base point you pick, they're going to be all isomorphic. This actually acts on the cover X tilde. And it acts in such a way that actually this is the Galois group of this cover X tilde. So in this sense, you can really think of this pi 1x, this fundamental group, as a Galois group. It's the Galois group of this cover X tilde of X, where X tilde is the universal cover. And finally, one of the things that we saw about this action is that this fiber is given quite simply. Okay, so firstly, the fundamental group acts transitively on it. So of course, as a G set, this fiber will be isomorphic to a quotient of this G. And in this case, the quotient that you take is you mod out by the fundamental group of the thing upstairs. But since that's simply connected, that's just the identity, which means that, in fact, this fiber above any point is isomorphic as a G set to that fundamental group G. So I'm not going to prove this theorem, but it sums up all the nice results about universal covers. So the most interesting thing is to ask, well, this is nice to have this definition so that you have all these nice properties, okay? But how can you guarantee that such a universal cover exists? And that's given by the following theorem. Suppose now our topological space X is not only connected and locally path connected, but it's also semi-locally simply connected. Then indeed it has a universal cover. And what I want to do is not prove this theorem, but I want to sketch how you actually do the construction, because it's actually quite a beautiful idea, and it's quite geometric in nature, and it follows from a lot of the ideas that we've been talking about earlier in this playlist. Okay, so to try to motivate the construction that's going on here, let's look at the example of a simply connected cover that we have, which is R covers the circles. That's given by this map here. Okay, so what we want to do is basically think, okay, we know this is the answer that we want, this R, but if we just wanted to work with what's downstairs here, okay, with just this base space, how can we construct the thing upstairs? Okay, so that's the question that we want to have a look at. Okay, so let's work towards that. So to work towards that, suppose we want to build this as a set firstly. So in particular, we want to build a particular point here. Okay, so how can we do that? Well, to get at that, I guess one thing that you can do, since this top space here, if it were to exist, it's going to be path connected, so we can join it to some fixed base point here. Okay, so we'll just fix some base point. Okay, so let's make a path going from there to there. And then we just continue that path there to there. Okay, what's nice about this is that when you look at this path, you can look at its image downstairs on X here. So in this case, it will go around like this. Okay. So this path downstairs is something that you can define purely in terms of the topological space downstairs. Okay. So that will give you some way to at least just have an approach to thinking about what this point is. But of course, what you must have noticed is that there are lots of paths going from here to here. Okay. But the point is that now, since this is meant to be simply connected, any two paths have to be homotopic to each other. Okay, and if they're homotopic to each other upstairs, they're going to be homotopic to each other downstairs. Okay, and what we also saw is that if we do have a cover, remember, if you have a path downstairs, you can lift it to a path upstairs, and if there's a homotopic between paths downstairs, it lifts to a homotopic path upstairs. Okay, so those sort of notions correspond. Okay, so hopefully you can see now what ought to be the construction of this simply connected cover. Okay, so what we're going to do is we're going to start with this downstairs on X. We're going to look at the set of all paths, okay, starting at X0. Okay, so in the case of this circle, we'll take the circle, we'll look at paths starting at X0. Look at the space of all of them. Okay, so in other words, the continuous maps from this topological pair from the interval 0, 1, 0 to X0. So this continuous map from 0, 1 to X, such that the 0 maps to the base point X0. Okay, so you can look at that, and that's topological space. Of course, that's too big. So what we want to do is we want to mod out by the ones which would be homotopy equivalent to each other upstairs. And we know that if we do have a cover, that corresponds to being homotopy equivalent downstairs. So that's the equivalence relation that we want to put on this set of paths. Okay? So we'll put an equivalence relation. Okay, so two paths, omega prime and omega, they're going to be equivalent to each other if the concatenated loops, so suppose you have two paths like this, omega here and omega prime like that. And let's look at the concatenated loop, which means omega prime star omega inverse. That means you go along one of them, and then you come back along the other one. If that is homotopic to the trivial path, then we'll say that this omega and this omega prime, those two are going to be equivalent. Okay, and that's our definition of our topological space X tilde. Okay, so it's a quotient of this topological space here. And I guess the final ingredient to actually give the data for a cover is to give the map from this x tilde to x. But let's just see where it is from the picture that we have here, which motivates what's going on. Okay. So here we have a path, and it's meant to correspond to this point here that has a path like this, lifted up like that. And of course, where should this path map to? Down on here. Well, where does this point map to? It's just the end of the path. So all we have to do is to map this space x tilde, okay, down to x, is we take this omega, okay, and we look at the end of the path. And of course, the end of the path will be inside x. That's the value that we want. Okay, so this turns out to be the construction for the universal cover under these hypotheses. Okay, that's when it has a universal cover. And you can see that it's a very, very natural, pretty construction. So the final thing I wanted to tell you about is just to give you a little sanity check. Of course, I won't prove this. You kind of see that it ought to give you the right answer. And as a quick sanity check, what I'm going to do is I'm going to look at this construction and we're going to say, well, okay, if this were true, then it should have these properties, right? So in particular, if you look at the fiber above the base point, x0, you should just get the copy of this group, the fundamental group downstairs. So let's just see what's going on here. What do you have? Okay, so what's the inverse image of x0? Okay, so what are the things which map to x0? That means that the omega 1 has to be at x0. So they're paths that don't just start at x0, but also end at x0. So they're just paths from x0 back to x0. Okay, and then we want to make sure that we put the equivalence relation on that. And what's that? That's basically up to homotopy. So you're just looking at homotopy equivalence classes of loops based at x0. And of course, that's just the fundamental group. Okay, so that certainly checks out. So that gives you a clear picture that this is exactly, this x tilde is exactly the size that you want it to be. Okay, so basically, it's a many-to-one cover of this base space x, and what's that cardinality of all those fibers? It's exactly the fundamental group. That's how you construct the universal cover. I hope you enjoyed this adventure in pure mathematics.